Hello everyone. Today we're going to go through the last lecture of magnesium and its alloys. I hope now you all know different magnesium alloy systems. Again, if you have any questions, please feel free to drop me an email. Right, in this lecture we're going to go through the following topics. First, we will cover some forming processes in magnesium industry like corrosion, extrusion, and forging. Second, I will just introduce different joining techniques in magnesium alloys. Third, we will focus on corrosion problems of magnesium alloys, since the poor corrosion resistance of magnesium alloys has been their Achilles heel, restricting their application in several sectors. In the end, if we have time, I will disclose the secrets of flammability of magnesium alloys. During the whole lecture, I will also give some examples of magnesium alloys and their applications. Wrought magnesium alloys attract special interest as lightweight structural material due to their homogeneous microstructure and enhanced mechanical properties compared to as cast alloys. However, due to the hexagonal crystallities, poor formability has been the biggest challenge in wrought magnesium alloys. As we mentioned in the previous lectures, at room temperature, the active slip substance of magnesium alloys is the basal slip, where slip takes place on the basal plane in the 1,1/2,0 direction. If the grains are in a twinning preferred orientation, whereas twinning can occur including 10/112 tension twinning and 10/11, 10/13 compression twinning. But at high temperature around 250 Celsius degrees, pyramidal and prismatic slip systems can be activated. This means magnesium alloys are more workable at elevated temperature rather than at room temperature. Generally, magnesium alloys can be produced in sheets, plates, extruded bars, shapes, tubes, and forgings. Unlike aluminium, for which cold rolling is usually the final step in sheet production, hot rolling is usually carried out for magnesium alloys in the temperature range between 300 Celsius degrees and 500 Celsius degrees, depending on the alloy and the pretreatment of the feedstock material. Large grains of 200 and 300 microns in the slab can be reduced by warm rolling to the final crystallized grains between 5 and 25 microns for a sheet thickness of 1 to 3 millimeters. If the rolling temperature or thickness reduction rate is not enough, dynamic recovery and static recovery only happen. However, if the working temperature and or thickness reduction rate is high enough, normally dynamic recrystallization and static recrystallization takes place and fine grains can be produced after rolling. This is very composition sensitive. Sometimes dynamic precipitation happens during hot rolling. The rollability and formability of magnesium alloy sheets is significantly influenced by hot rolling parameters, such as temperature, thickness reduction per pass, rolling speed, and alloy composition. At higher temperatures, more deformation modes such as non-basal slip and compression twinning become activated and operative during hot rolling process. Wrought magnesium products have particularly strong fiber texture. In general, the basal pole in wrought magnesium is found to be aligned near to parallel to the direction of predominant material contraction. Thus, in rolling, the basal plane is found close to the plane of the sheet, as demonstrated in top left image. So this texture is also called as basal texture. The bottom left image is a typical inverse four-figure EBSD map of magnesium Az31 alloy after hot rolling. We can see most of the grains are color-coded in red. This means most grains have their z-axis parallel to 0001 directions, which give the sample a strong basal texture after rolling. The mechanical properties of magnesium sheet metal are mainly determined by the final grain size. Beneficial thermomechanical reactions can be achieved by adjusting work hardening, recovery, and recrystallization effect, which are sensitive to alloy composition, process temperature, deformation parameters, reheating cycles, the final cooling to room temperature, and an additional heat treatment. The right images clearly demonstrate that magnesium alloys can be successfully rolled into sheets in lab and industrial scale. One of the biggest challenges of magnesium sheet is the anisotropy of their mechanical properties. The figure shows engineering tensile stress strain curves of the magnesium zinc calcium alloy subject to tensile tests along the RD, 45 degrees to the RD, and the TD. The alloy shows quite different tensile properties depending on tensile loading directions. It shows that both yield and tensile strengths are highest along the RD, followed by 45 degrees to the RD and the TD, while negation values show the opposite trend. Here I want to say RD is short for rolling direction, TD is short for transverse direction. This table lists tensile properties of ZEK100 with different alloy additions tested along the RD, TD, and at 45 degrees to the RD. In general, all rolled sheets exhibit an anisotropic yield response. For example, yield strength differential between the three loading directions, which is typical for conventional magnesium sheet. It is clear that sheet anisotropy is influenced greatly by alloy additions, even for the similar alloy systems. For example, ZK100 sheet with different rare earth element additions have quite different levels of anisotropy after rolling and annealing. The yield stress obtained along the RD is much higher than that obtained from the TD. The ductility is lowest for the RD and the greatest for the TD in all alloys, except for the serine-containing alloy. The highest ductility, together with an ultimate tensile strength of 233 MPa, is achieved in the gadolinium-containing sheet that was tested along the TD. The neodymium additions leads to isotropic ductility, 0.28 for the RD and 45 direction, and 0.29 for the TD. All these mechanical properties changes can be correlated with the microstructure, for example, texture. Sheet forming process involves stretch forming and deep drawing, in which magnesium sheet undergoes a variety of stream paths. Stretch forming and deep drawing are often used to obtain information about specific features of the sheet formability. The next figure shows the stretch formability of different magnesium alloys measured by the Ericsson cupping test at room temperature, which is indicated by limiting dome height (LDH) values. The stretch formability of magnesium alloys containing rare earth elements, lithium or calcium, as well as the texture-modified Az31 alloy, is better than or comparable to those 5 series and 6 series aluminium sheet alloys at a similar strength level. In general, the stretch formability of those magnesium alloys that have low yield strength, for example 100 to 170 MPa, is comparable to that of some commercial aluminium alloys. But higher strength magnesium alloys exhibit poor stretch formability. However, after suitable alloy composition optimization, some magnesium alloys can obtain both high strength and excellent formability. For instance, the alloy AZMX1110, after adding a small amount of manganese and calcium, the limiting dome height is nearly 3 times of the commercial Az31 alloys as shown in the right figure, and the yield strength is about 50 MPa higher than Az31 too. This set of images give the examples and perspectives of magnesium sheet. A shows a prototype bumper beam, B bracket element, C seat component, D inner door panel, E hybrid aluminium magnesium engine bonnet, F prototype car with magnesium sheet roof, G sandwich component, interior covering panel, H prototype front fender, I magnesium tailored blank. The point I'm making here is, although currently magnesium alloys only account for 1% of the total weight of a car, they have huge potential to be used in cars if promising magnesium alloys can be developed in future. Extrusion is the process by which a block or billet of metal is reduced in cross-section by forcing it to flow through a die under high pressure. The two main advantages of this process over other manufacturing processes are its ability to create very complex cross-sections and to work materials that are brittle because the material only encounters compressive and shear stresses. As with aluminium, magnesium billets are extruded into profiles of various shapes using extrusion techniques. The direct and indirect methods are the two preferred magnesium extrusion techniques. In most instances, the direct extrusion process, as described in the left image, is employed for magnesium alloys. The container, dummy block, and die are kept at the same temperature as the billet, but 25 to 50 degrees Celsius below the extrusion temperature. Various plane and hollow shapes can be produced using the direct process. Tubes can be produced by extruding a hollow beneath over a centered mandrel located inside the main ram. In indirect extrusion process as depicted in the image, the die at the front end of the hollow stem moves relative to the container, but there is no relative displacement between the beneath and the container. So this process has no friction between the beneath surface and the container. Very often, the indirect extrusion is used at the start of the direct extrusion process because the friction force is eliminated. The final extrusion phase is usually carried out by the direct extrusion method. Extrusion of magnesium alloys is a typical case of hot working practice, where a heated beneath is deformed into the required shape at a rate determined by the process equipment. The strain rate time profile is usually defined by the process. Hot working operations such as extrusion are conducted in a high strain rate range of 10 to the power minus 3 to 10 to the power 3 per second and develop relatively high stresses. Under hot working conditions, all forms of softening process occur, named static recovery and recrystallization, and dynamic recovery and recrystallization. Some possible combinations of dynamic and static softening process during hot working are shown in the left image. More specifically, depending on working situations, sometimes dynamic recrystallization can happen in the chamber, and static recrystallization occurs at the exit of the mold, while sometimes static recrystallization was delayed. The right figure shows the microstructure and texture of an extruded AZ31 alloy. The extruded alloy exhibited a fully dynamic recrystallized and homogeneous microstructure with an average grain size of 60.7 microns. The 0001 pole figure and corresponding inverse pole figure reveal a typical non-fiber texture without specific crystallographic directions parallel to the ED, in which the texture components tended to distribute homogeneous along the arc between 10 bar 10 and 2 bar 1 bar 10. Compared to aluminum extrusions, the extruded magnesium products often have tension-compression yields asymmetry. For example, this figure shows the compressive yield strength is only half of the tensile yield strength in extruded AZ31 alloy. Such problems have to be solved for any larger usage of magnesium extrusion alloys. The main reason for this is magnesium extrusions develop a strong texture during processing. The basal planes, randomly oriented grains, are rotated so that they are approximately parallel to the extrusion direction. For example, the 10 by 10 axis parallel to the extrusion direction. Thus, the magnesium extrusions normally have a strong fiber texture. For this type of texture, basal slip is not favored under both tension and compression loading along the extrusion direction. Instead, 10/12 twinning occurs readily upon compressive loading, and the yield stress is much lower than the tensile yield stress. This table lists the tensile and compression strength of extruded bars of magnesium alloys. For AC alloys, tensile yield strength obtained from a direction perpendicular to the extrusion direction is 30 to 40% lower than that measured in the extrusion direction. In comparison, the difference for ZK alloys is significantly smaller, particularly when the alloy has a higher alloy content and is in the T6 condition. The commercial magnesium alloys WE43 and WE54 do not suffer from the yield strength anisotropy problem. Their tensile properties are quite uniform when tested along the directions parallel and perpendicular to the extrusion directions. Again, suitable composition is key to adjust the mechanical properties in magnesium alloys. Commercial extrusion alloys like AZ and ZK series alloy can also be forged into high integrated components using hydraulic presses or slow action mechanical presses. Forging is normally done within 55 Celsius degrees of the solidus temperature of the alloy. There are several advantages over commonly used die-cast magnesium parts. First, excellent strength, especially with the fibers lying parallel to the main load direction. Second, very good properties for pressure-sealed components by preventing a porous microstructure. Third, the components can have complex geometries while several forging steps. The image shows a forged magnesium wheel made of ZK31 alloy. As you may already know, that forged or casted aluminum alloys are the main source of current car wheels. Compared to forged aluminum wheels, magnesium wheels are much lighter, but the strength is lower and the number of load cycles is not competitive to forged aluminum wheels. In addition, the bottom table also shows the properties of the samples collected from different positions of the wheels are quite different, which needs to be addressed to extend magnesium application in the car wheels industry. In addition to the use of extrusion and sheet metal processes, die casting in particular is an especially important method of producing thin-walled, highly integrated components. The integration of die-cast components into a vehicle structure required joining techniques that offer the maximum use of the materials of the joined parts under operating loads. Magnesium poses high demands on the welding process because of its physical properties. Magnesium alloys show a relatively broad melting interval of about 420 to 620 Celsius degrees. In combination with low melting eutectics, the risk of hot cracking needs to be taken into account. Here we show several welding and bonding techniques in this slide. TIG welding is short for tungsten inert gas welding, and MIG is short for metal inert gas welding. Other welding techniques used in magnesium alloys include laser beam welding, electron beam welding, friction welding, and diffusion bonding. The oxide layer exists on the surface of magnesium alloy is one of the causes of pore formation in the weld bead. Generated pores in the weld bead deteriorate the mechanical properties of the weld, especially the tensile strength. A prerequisite to obtain the excellent corrosion properties of current magnesium alloys is careful control of the impurity levels. Elements such as iron, nickel, and copper are highly detrimental to corrosion properties. In moist air, magnesium-based materials naturally tend to form a thin, less than 1 micron, passivated surface layer, which consists mainly of magnesium hydroxide, MgOH2. MgOH2 does not become stable until the pH value is greater than 8.5. This explains why magnesium, in contrast to aluminium-based materials, does not dissolve in alkaline media. The passivating layer on the magnesium is not dense. Even from a theoretic point of view, it's the degree of coverage obtained from the quotient of the specific higher volume of the magnesium hydroxide and the mechanical magnesium is less than 1. This quotient, which is referred to as the Pinin-Bedworth ratio, has a value of 0.81 for an existing passivated layer consisting mainly of magnesium hydroxide. If a value of less than 1 is obtained for the degree of coverage corresponding to a natural passivated layer, this indicates that the underlying metal is not completely covered. This allows corrosive substances to enter as far as the magnesium-based metal, thus resulting in corrosion. In general, corrosion rates of magnesium in rural and industrial areas lies between aluminium and mild steel. The metallurgic factors affecting the corrosion performance of a magnesium part are the alloy composition and microstructure. The alloy composition refers to both the intentional constituent and the common contaminant. The microstructure factors are the grain size and alloy temper or heat treatment effects. While these factors are interdependent, the figure shows the corrosion behavior of different alloys after source fork testing. It is evident that Az91C has the worst corrosion resistance compared to We43 and Az91E. Az91C is used in sand and permanent mold castings when maximum corrosion resistance is not required. Az91E is a high-purity alloy with excellent corrosion resistance used in pressure-tight sand and permanent mold castings. This confirms corrosion resistance is rarely composition and microstructure sensitive. For the big casting components, the same results can be obtained after source forking testing. Az91C was severely corroded, while Az91E only had some surface pitting after 10 days testing. Recently, a high special strength and corrosion resistance magnesium lithium alloy was designed. We can see from the left image that the magnesium lithium-based alloy's corrosion resistance is even better than pure magnesium. Following appropriate thermomechanical processing, The high lithium content alloy described by Ferry and co-workers exhibit passivity and a remarkably low corrosion rate. Magnesium does not spontaneously form a protective oxide layer. Instead, the alloy forms a protective lithium carbonate surface film by reaction with atmospheric CO2. The small and finely dispersed lithium-rich zones promote the formation of the protective lithium carbonate film, and the absence of relatively coarse second phases or intermetallic particles prevents conditions that typically degrade alloy corrosion resistance resulting from microgalvanic interactions between the particles and the matrix. Magnesium is highly flammable, especially when powdered or shaped into thin strips. Magnesium powders are usually designed and used in flares. For example, magnesium powders can be added into fireworks. Magnesium powder can be also used in propulsion systems. For example, powdered magnesium carbon dioxide combustion is examined as a potential residual propellant combination for Mars propulsion by NASA. However, don't panic. Starting a fire for magnesium is not easy. The temperature must reach melting point, must sustain heat source to overcome conductivity, must have oxygen or CO2, and solid magnesium is not easy to burn. While magnesium products have been used in military aircraft for many years, they have little use in civil aircraft interiors due to flammability restrictions from the U.S. Federal Aviation Administration (FAA). In 2013, the results of the magnesium full-scale testing and the progress demonstrated in the development of the lab-scale test method led FAA announced that it would now allow magnesium in aircraft seats. The figure clearly shows W43 and electron-21 did not burn when melted, while AZ31 was burned when melted. W43 and EV31 are the only two alloys that have passed extensive flammability tests conducted by the FAA, including 7 full-scale airplane interior tests. Magnesium Electron started producing compatible seats with major structural components made from W43. These seats provide a significant weight reduction compared to commonly used aluminum alloys, and the first batch are scheduled to enter service in the near future.